All right, well, let's get this show on the road. My name is Sherry Sparks. These are my co-speakers, Sean Embleton and Ryan Cunningham. Our presentation today is titled Sidewinder, an evolutionary guidance system for malicious input crafting. I think there's something wrong with the mic here. All right, that seems better. Okay, all three of us were graduate students of computer science at the University of Central Florida. And our talk is going to be about malicious input crafting. We like to make this analogy between malicious input crafting and firing missiles. Traditional black box malicious input crafting, like I'm sure everyone here is familiar with the term fuzzer, is not particularly intelligent. Basically, you throw inputs at a program and you monitor it, hoping for some unexpected behavior or some kind of a crash to occur. Well, it may take a lot of random inputs to be thrown at that program, or a lot of unguided missiles before that program crashes or we actually get anywhere interesting. So the three of us wanted to explore this idea of, is it possible to improve upon this black box fuzzing methodology and turn these unguided missiles into sort of guided missiles? And that's kind of the basic concept for our talk. So I'm going to go ahead and get started here. Pretty basic definition, software vulnerability, taken right off Wikipedia. Refers to a weakness in a system allowing an attacker to violate the integrity, confidentiality, access control, availability, consistency, or audit mechanism of the system. Software vulnerabilities may exist only in theory, or they may have working exploits. And so therefore it becomes important kind of to make this distinction. You can have a program that uses, for example, traditionally vulnerable API calls that are vulnerable to, usually to buffer overflow and such. And, it may not be possible to actually exploit those vulnerabilities. So we have this sort of differentiation between a potential vulnerability, that being a location within a program that contains a known weakness, like a potentially vulnerable API call, and an exploitable vulnerability for which you can actually craft some kind of a working exploit. In order for a vulnerability to be exploitable, a couple of conditions need to be met. The first condition is usually that program location needs to be dependent upon user-supplied input. The second condition, of course, is that location needs to be reachable on the runtime control flow graph. So traditionally in the vulnerability analysis and discovery process, there have been several methodologies that have been employed. The first methodology is your traditional white box analysis. This is also known as glass box testing or structural testing. It simply involves disassembling a program manually, human reverse engineer going through, manually understanding the control flow and the program logic. The benefit is that the human mind is good at pattern recognition. The human mind is more likely to find subtle bugs that a more automated tool would miss. Of course, the drawback is that it's very time-consuming, and time is money, as we all know, so it could also be very costly. Secondarily, it can sometimes be difficult to tell if that potential program vulnerability will be reachable at runtime, and also what is the structure of that input that will allow you to reach that vulnerable location in the program. So kind of the opposite of white box analysis is black box analysis. This is known as concrete box testing or functional testing. Black box analysis does not rely on human understanding of the source or disassembly. It's usually fully automated. And it involves injecting random or pseudo-random input into a program and then monitoring its output for crashes or otherwise unexpected behavior. The benefits of the black box approach is that it's easily automated. And also your vulnerabilities discovered at runtime are definitely reachable, and you know what the input structure was that caused you to get there. The drawback is that the random nature of the input space exploration is going to make your probability of discovering that vulnerability highly non-deterministic. So one common black box tool is the fuzzer. Fuzzers have been used to find a whole lot of vulnerabilities recently, especially in like parser or protocol handling logic. Fuzzers are kind of the definition of black box in the sense that they inject malformed input into a program and then monitor it for crashes. A lot of bugs are the result of programmer oversights regarding assumptions about the structure of your user-supplied input. So these fuzzers are often used to find bugs in parser and protocol handling logic. Some examples of fuzzers that are in use would be Spike from Immunity. File Fuzz was created by the iDefense guys and presented at BlackHat last year. And then Peach Fuzz, which is a framework for building your own fuzzers. Fuzzers they're good tools. They've been used to find a lot of vulnerabilities, but they're kind of a double-edged sword. There's good points and bad points. The good point is the fact that fuzzers are fully automated software attack tools. They don't really require much human intelligence to drive them. And also, the random or pseudo-random input selection results in fairly widely sampling the input state space. And they may generate, inputs that a human might not think of. The bad news about fuzzers is that they're not very intelligent. That is, we keep throwing these unguided missiles, so to speak, at a program and, and hoping that program will crash. But we don't really, over time, learn anything from the inputs that we've tried in the past that would have any hope of driving our input selection in the future to improve our chances of getting somewhere interesting in that program. So therefore, we don't have a good measurement of attack progress. The program, it either crashes or it doesn't. Also, there's a non-deterministic time frame for finding an interesting bug with, throwing random inputs or unguided missiles at this program. So, our program has an equal likelihood of crashing, 2 minutes from now or 2 months from now. So the question is, can we try to mitigate some of these shortcomings of traditional fuzzers and come up with some ideas that can maybe help to create a smarter fuzzer in the future? So our goals on this project were, one, to come up with something that would have a fuzzer enable it to learn from past inputs that it has tried to improve future input selection or to improve input selection in the future. We'd also like to improve the odds of finding something interesting within a reasonable time frame. Obviously, throwing random inputs at a program is going to take a lot of random inputs before you potentially get somewhere interesting or make the program crash. So if we could maybe drive our input selection a little more intelligently, maybe we could somehow reduce the time frame and make things a little bit more efficient. And then, of course, our third goal is to keep the attack as automated as possible. We don't want to revert back to more of a white boxed analysis approach. So the question is, what can we learn? What could we use to drive a fuzzer? We can make the first observation that the runtime execution trace is dependent both upon user-supplied input and the static structural characteristics of the control flow graph for the program. A normal fuzzer, as we said, driven by random input injection, has no knowledge or measurement of how much or what portions of the program and input state spaces have been explored. Perhaps if we had this information, we could use it to choose better inputs in the future based upon what we've tried in the past. A few things to consider. Greater code coverage may correlate to a greater chance of discovering a vulnerable program state. By linking inputs with their runtime execution paths, we may be able to select for those inputs that have a greater likelihood of taking specific dependent execution paths towards areas of the program that we suspect may be interesting or may have some usage of APIs or other types of vulnerabilities. So in terms of input crafting, here's just an example. Say, for example, we have some kind of a packet parsing routine that takes in a packet via the receive function. And following that taking of input through the receive, there's some kind of parsing and validation logic on the execution path. And at some point along in that logic, there are some areas that we suspect maybe, have some kind of vulnerabilities. A simple example being maybe, some string copy out of some data that has been supplied by the input buffer for like a packet or something. So the question is, what does the input have to look like for us to exercise that code path that leads between the receipt of our input from the user through the packet and the and exercising that vulnerable string copy on some code path. So how can we figure this out? Well, we can disassemble the program. We can manually decode the parsing logic. That would be your white box test. We can throw random inputs at it, hoping we will eventually get there, maybe, and hopefully that we might eventually, and that will be your black box test. Or we can try to improve a little bit and use some kind of heuristics or intelligence to hopefully push our program execution towards that state. So maybe we can model this kind of problem as sort of a search problem. First of all, what if we could automatically decode the packet parsing logic? We're throwing inputs into a program, but those inputs need to correspond to some kind of a structure, usually, for it to get past the parser logic. So what if we start out and we don't really know what the structure of that input is exactly? Can we kind of evolve an approximation of it heuristically? That's kind of one question here. And then can we model this input crafting as more of a generalized search problem? That is, in some sense, aren't we searching for inputs that conform to a structure capable of taking certain dependent execution paths in the program control flow graph? Certain areas of the program that we think may be interesting or have a greater than average chance of leading to some kind of a vulnerability. So we have tried to perform this search by driving input selection using a genetic algorithm, where the relative fitness or goodness of a specific input is related to its progress on the program control flow graph. So here's the basic idea. Over time, some inputs will be better than others. How will they be better? Well, one, they may increase code coverage so that they reach previously unexplored areas within the control flow graph. And secondly, they may be on a path to some interesting area that we wish to explore further within that program, where we suspect some vulnerability may lie. So if we take these inputs, these more fit or better inputs, and we mate them of all the ones that we found in the past, then perhaps we can select for those characteristics in the future that maximize code coverage and drive inputs down execution paths past parsing and validation logic towards areas in the program control flow graph that we think may be interesting and we want to explore further. So first, a little theory. I'm going to turn control over to Ryan Cunningham, and he's going to talk about genetic algorithms.
Hello everyone, can you hear me? So the theory that is incorporated into Sidewinder is actually, if we were to cover every topic specifically, it could be the subject of basically a whole semester-long graduate course in computer science. So I'm going to try and cover them as intuitively as possible without confusing you. So first, we're going to discuss genetic algorithms. This is what we're using to solve this input crafting problem. So what is a genetic algorithm? It's a type of algorithm that mimics evolution. Algorithm and evolution are two words I think that people use a lot, but I think don't have a precise understanding of what they mean. So I think we should cover some ground there first to lay the groundwork later.